Welcome back. We made it to chapter 4 of Kuchemann, and this is a fun chapter. It starts getting into kind of more practicalities. And first thing, though, it actually returns back to a little bit of sizing. And so, beforehand, there was just sort of this weight of the engine for the aircraft, and, it just sort of said, hey, this is roughly 0.1. But now that we've got a little bit more details on the engine, we have some theory behind it, it's a little bit of a return back to that. And so one of the ways to do it, though, is actually tied into the lift over drag. And so we know that for a given aspect ratio, right, and I apologize again here for lowercase s over uppercase s, that's the aspect ratio. We know that there's a maximum L over D, and that occurs at 1/2. There's a pi, the aspect ratio, and then divided by the K over CDF. Okay, so pictorially, though, this is looking like this. There's some sort of maximum L over D, and this is a function of, usually this is plotted here as a function of lift coefficient. Sometimes you might see it as plotted as an angle of attack, but it's kind of a maximum. Now what's interesting, though, is they then say, let's then define L over D as some fraction L over D max. And presumably you could go greater than 1, but in practice what happens is that usually you're only concerned about sort of this side of the equation, because in the end you're not maximizing range, you're not maximizing L over D, right? In the end you're actually maximizing payload. And so you come back to this engine analysis and realize that, I'll kind of plot it in orange along this graph, there is there's a drag due to lift that's going up as this thing goes quadratic. And so presumably, and then what happens in practice is that you always end up designing your aircraft running shy of L over D max. Now, the way they then do it, it's a little, I had to go derive it myself, not too much fun. You're welcome to go do it. But based on this formulation, you can actually then get CL, and it looks like 1 over n, 1 minus square root of 1 minus n squared times CL max. Okay, and this is not, it's not that most useful of a formula. The minus is actually because it's the minus half of this, you actually get a quadratic, and so that the plus would be on the plus side here. And then the engine curve, if you then go upon doing it, so that they define that the weight of the engine, and they say C3 times the thrust over 1/2 rho at cruise and v at cruise squared. Now, kind of used to C's being constants. It's a little bit annoying that it's actually not a constant based on, that's a force and that's a pressure. And so really this has units of pounds per square feet or yeah, it's not useful. Then if you go through and do weight of the engine, you normalize it with weight, at least a couple things fall out. And so I'm going to write like this. There's a factor of 2. There's the friction component. And then here's a C3 over wing loading. I group it like that. Kuchemann doesn't, because in the end, I'd rather have my C3 be a constant. So I'd rather just know how is C3 compared to wing loading. That's helpful for me. And then you get this 1 over n squared, 1 minus square root of 1 minus n squared. Now, the Kuchemann does have a couple plots on this, but the important one, and I'll just graph it here kind of with my pen. The important one is that you're looking at payload with respect to maximum. And if this is range, and this is n, you end up having something that looks like this. And so the maximum payload for short range is actually a smaller n than for longer range. N is much closer to 1. So anyways, it seemed a little silly of how to do it, but in the end it kind of comes down to like But this is not good enough. Just saying the engine's 10% is not good enough. The engine is ultimately the one that's countering drag in cruise. And so, depending on the drag, it's basically this form is gonna hurt. So while your L over D may go up, which might mean your range goes up, your engine size also then has to go up, and that may not be good for payload, which is what this is showing. Okay, and so I went back and I plotted a couple things just particularly for us. Now, the first one is actually this. I went back and did a little bit more modeling, kind of using some of the equations from Chapter 3. And so I have here a solid rocket motor, liquid rocket motor, rocket engines, and then this blue sort of band represents the bottom edge of the band is actually what we've achieved at Venus from a detonation engine performance. Now, to be fair, the liquid engine line here I'm keeping as jet fuel and peroxide. If it would be much higher if it was, say, liquid oxygen and methane or something like that, or liquid oxygen RP. And then I kept the turbojet in max, so afterburning turbojet on there. And then I added some bands now for both the ramjet and scramjet, picking Mach 2.0 combustion for scramjet. And I wanted to slice this band up a little bit into a couple air temperatures point of view. And so the first band here is actually sort of the assumed, understood auto ignition temperature of jet fuel. So presumably, you can't just turn a ramjet on until you hit this. And that represents kind of this 3.5 Mach number, which is about what people are doing. Now, some people will say maybe you can pull that to the left. Okay, no problem. But then again, with the ramjets, the air temperature as you're going higher, so your compression's going up, which is good. That's actually why the ISP is going up a little bit here. And then, and again, normally the way to plot it's not with ISP. Normally, the way to really think about this is propulsive efficiency, but showing here for ISP, that this is then the air temperature. And so, what I'm putting here is this diamond is saying, we might be okay with the entirety of our engine innards being Inconel. And so 1700 Fahrenheit would be okay. Maybe not. Maybe you want to have titanium or stainless steel and you would back this up. And so it's kind of the difference between flying at a Mach 4 condition versus flying at, say, a Mach 4.75. Mach 5 is going to be hot, right? If you actually really wanted to fly Mach 5, your engine's going to be pretty toasty. Okay, and then because again, the temperature of slowing that air down. If you slowed it down to Mach 2 and you went ahead and tackled scramjet combustion, then these would be air bands. So that, again, the first band here would be stainless steel titanium innards, so that would get you to Mach 5.5. And then if you wanted to go again Inconel, you could probably push it to 6.5. So that's kind of the ISP. And then what I'm then going to show on these curves, kind of coming back to the engine sizing, I'm actually going to show, hey, if we assume this blue line from an ISP point of view. Now, that ends up giving us a sort of mission ISP, an ISP up to cruise of about 850 seconds. And that includes, when I say cruise, that includes the penalty of drag as well, sort of estimate there. And then I'm gonna give turbojet effectively an ISP of 1800 when you see this kind of turbo-based combined cycle. Now, what you end up seeing, and I'll do kind of two different plots. The first one here would be a 30% dry mass vehicle. Again, it's just structure. That's not the full dry mass of the vehicle. This represents just it's not the engines and it's not the stuff to hold the payload. And that's that 30% would be what Kuchemann was referring to, C1 calculations. I put C2 as 2.0. We've seen that it's really kind of 2.5. That might be with furnishings, but let's just go with it. You could probably lighten some things up, or maybe at first we're talking about a drone, so there's no furnishings. So a couple things that really jump out. The first one is that here's solid rocket motor. So I'd be using a solid rocket motor, sort of 280 seconds all the way up to ram start, and then doing a solid fuel ramjet. And the solid fuel ramjets, both this curve and this kind of lighter teal curve, I did give them the benefit of lower drag. It's a more dense fuel, and so the drag would be beneficial. On turbine-based combined cycle, basically I used the values for RDE plus liquid fuel ramjet. For turbine-based combined cycle, so your engine's double. That's a big, huge engine. And then there's about a 30% penalty on drag because that engine takes up quite a bit of volume. Remember, drag goes like volume squared, and so roughly saying that there's a 10 to 15% increase in the volume of an aircraft with a turbine-based combined cycle. And then, there if you go through the ISP calculations, again, I used about 1,800 seconds for the turbine-based combined cycle ISP. It does take about 5% less fuel to get up to boost. Okay, so that would be 12% fuel versus, in our case, on the liquid fuel, the RDRE, and then also igniting that ramjet early, we use about 17% to get up to fuel. And so a couple of interesting things that show up, those people trying to do turbine-based combined cycle are targeting the Atlantic market, and that would give you maybe a 3 to 5% payload. So not great. That's okay. That's not great. More likely, 2,500 or even 1,000. But this, it really shows, just kind of jumps out that no, the detonation engine is really the winner here. So even at a 3,500 mile, that's just shy of 10% payload. So that would be, say, an Atlantic crossing, and then here's a Pacific crossing at 5,000 miles. And so we would still have halfway decent payload. So again, on a 5% payload on 50,000 miles, right? So if this is a 100,000 pound vehicle, 5% payload, that's 5,000 pounds. We would estimate that's roughly 10 people. 500 pounds is usually what you use kind of per person for all the kind of stuff, keeping them alive. Now, I'm kind of double counting here because really it's to be determined if the stuff to keep the people alive, if that's already included in this payload, or if I'm double counting. Right? So likely I'm double counting a little bit, and so I would look at this and say, hey, this shows that our system should be able to cross the Pacific and do well. Now I put the RDE plus the solid fuel ramjet on there. Again, just if you're making a weapon, you're not really concerned about the refuelability of the weapon, and so maybe it makes sense you get a little bit more payload, or maybe it's a little denser. It could be a system trade, but in the end, it's both. If you compare this curve versus the solid rocket motor, in the end, it's ultimately like, yeah, you're able to get to ramjet. I think solid rocket motor here used 45% of its fuel to get to ramjet, so it's a pretty big jump. Okay, so that's the first part of Chapter 4. I actually really I thought it was strange. I thought this first part of Chapter 4 really should have been kind of appended onto Chapter 3, because it's really just kind of talking about the engine, but really most of Chapter 4 here is now talking about the practicalities of building real vehicles. So we'll see you next time.